June 6, 1912, 1 o'clock in the afternoon. In 3 minutes, 40 square miles of forest will cease to exist. The ground splits open. A column of superheated gas and pulverized rock shoots 15 miles into the sky, higher than any human has ever traveled. The roar can be heard 500 miles away. Avalanches of fire race down the valley at 100 miles per hour, incinerating everything in their path. Trees that stood for centuries vanish in seconds. Rivers boil away. The temperature exceeds 1,500 degrees. In 60 hours, 3 cubic miles of the Earth's interior will be expelled onto the surface. A mountain will collapse inward, creating a crater 2 miles wide. And where forests once breathed green, a desert will be born. A desert so desolate it will remain barren for more than a century. This was the largest volcanic eruption of the 20th century, and almost no one saw it coming. How does the Earth hide such fury beneath our feet? How does a landscape transform from paradise to wasteland in less than 3 days? And why does this desert, created by fire, still refuse to heal? Let us go back to the beginning, to a time when the land around Mount Katmai breathed green. There was a time when the land around Mount Katmai breathed green. Spruce forests embraced deep valleys. Brown bears walked among willows along crystalline streams. Salmon ascended the rivers in schools so dense the water seemed to boil with life. This was the Alaska Peninsula in the early 20th century, a remote sanctuary, untouched, where nature reigned absolute. Few human souls inhabited these lands. Small native communities, the Aleutic people, lived in ancestral harmony with the cycles of land and sea. They fished, they hunted, and they told stories around the fire. Stories of mountains that spoke, of spirits that dwelled in the depths of the earth. But the mountains indeed kept secrets. Mount Katmai, rising 2,047 meters high, stood majestic, seemingly asleep, seemingly peaceful. No one imagined that beneath that mask of ice and rock, unimaginable forces were accumulating. Because the earth, my friends, is not static. It moves, it breathes, and sometimes it screams. The year was 1912. Winter had loosened its grip on the Alaska Peninsula, and spring arrived with its customary promise of renewal. The Aleutic villages prepared for the salmon runs. Trappers checked their lines. Life continued as it had for generations, but the earth was restless. In early June, something changed. The animals noticed first, as they always do. Bears abandoned their fishing grounds without explanation. Flocks of seabirds wheeled inland, their cries sharp and urgent against an empty sky. Even the wolves, those patient hunters of the tundra, retreated to higher ground as if answering some primordial call that human ears could not perceive. The Aleutic elders watched these signs with growing unease. Their ancestors had passed down stories of mountains that awakened, of times when the earth shook and the sky turned dark. These were not mere legends whispered to frighten children. They were warnings, etched into collective memory across centuries. On June 1st, the first tremor arrived. Not violent, not catastrophic, merely a subtle shudder, as if the earth were turning in its sleep. Dishes rattled in the few settler homes scattered across the peninsula. In the village of Katmai, located at the base of the mountain that bore its name, people paused in their daily tasks, exchanged glances, then continued with their work. Earthquakes were not uncommon here, along the fiery rim of the Pacific. The Ring of Fire, scientists would later call it, that vast horseshoe of volcanic and seismic activity encircling the Pacific Ocean. The people of this land had learned to live with the Earth's occasional complaints, but this was different. The tremors did not stop. June 2nd brought more shaking. Then June 3rd. Each day the frequency increased. Each day the ground beneath their feet felt less certain. What began as occasional shivers became a constant, unsettling vibration. The Earth's heartbeat growing faster, more irregular, more urgent. By June 4th, the earthquakes were occurring hourly. Sleep became difficult. Nerves frayed. In the village of Katmai, families began gathering their most precious possessions, wrapping them carefully, preparing for a journey they hoped would not be necessary. The Aleutic knew. Some knowledge runs deeper than science, older than instruments. They understood that the mountain was speaking and its message was clear: leave. On June 5th, most of the residents of Katmai village made a decision that would save their lives. They loaded their boats, took what they could carry, and turned their backs on the only homes they had ever known. Some wept as they rowed across Shelikof Strait toward the village of Purryville, some 20 miles distant. Others sat in silence, watching the mountain recede behind them. They could not have known they would never return. Meanwhile, at the telegraph station in Kodiak, nearly 100 miles to the east, the operators noted the increasing seismic activity with clinical detachment. Messages were sent to the U.S. Geological Survey offices in Washington. Scientists reviewed the reports with interest, but not alarm. Earthquakes in Alaska were, after all, routine. What none of them understood, what none of them could understand with the limited knowledge of 1912, was the magnitude of what was building beneath their feet. Approximately 7 miles underground in a chamber of unimaginable heat and pressure, magma was rising. Not slowly, not gradually, but with accelerating fury. The Pacific tectonic plate, that massive slab of ocean floor, had been grinding beneath the North American plate for millions of years. Water from the subducting plate had seeped into the superheated mantle below, lowering the melting point of rock, creating magma, feeding the chamber that now swelled beneath Mount Katmai, like a wound about to burst. The pressure was becoming unbearable. The Earth's crust, that thin skin we walk upon so confidently, was straining under forces that could pulverize mountains. Cracks were forming. Pathways were opening. And in the early morning hours of June 6, 1912, the mountain could hold its silence no longer. What happened next would reshape the landscape for 100 miles. It would create a desert where forests once stood. It would bury valleys under hundreds of feet of ash. And it would teach humanity a humbling lesson about the power that sleeps beneath our feet. But that story belongs to what comes next. Before we continue this story, subscribe to the channel. Your support helps us tell the true stories of Earth's most powerful volcanoes. June 6, 1912, 1 p.m. Alaska time. The Earth split open, not at Mount Katmai as everyone expected. Not where the earthquakes had been centered. Not where anxious eyes had been watching for days. No, 6 miles to the west. A place that didn't even have a name on any map. The ground exploded with a violence that defied comprehension. The eruption began with a roar that could be heard 500 miles away. Witnesses in Juneau across the Gulf of Alaska reported hearing what sounded like artillery fire. In Kodiak, 100 miles to the east, people rushed from their homes, convinced that war had come to their shores. But this was not war. This was the Earth itself, venting fury accumulated over millennia. From a fissure that would later be called Novarupta, the new eruption, a column of superheated gas, ash, and pulverized rock shot 15 miles into the stratosphere. 15 miles, higher than any airplane of that era could fly. Higher than human beings had ever ventured. The eruption column punched through the troposphere and spread across the stratosphere like an expanding umbrella of destruction. The energy released in those first moments exceeded the atomic bomb that would devastate Hiroshima 33 years later. But this was not a single instant of violence. This was sustained, relentless, apocalyptic. The magma erupting from Novarupta was not the slow, flowing lava of Hawaiian volcanoes. This is something far more deadly. The magma was viscous, thick with silica, supercharged with dissolved gases. As it reached the surface and pressure dropped catastrophically, those gases exploded outward, shattering the magma into billions of tiny particles. What emerged was a pyroclastic flow, one of the most lethal phenomena in all of geology. Imagine an avalanche made not of snow, but of superheated gas and rock fragments, racing down the mountainside at speeds exceeding 100 miles per hour. The temperature within this avalanche reached 1,500 degrees Fahrenheit, hot enough to melt lead, hot enough to incinerate everything organic in its path. The first pyroclastic flow roared down the Yukak River Valley within minutes of the initial explosion. Trees that had stood for centuries were snapped like matchsticks, then instantly set ablaze. The flames lasted mere seconds before being smothered by the advancing wall of ash and gas. Animals caught in its path had no chance to flee. Death came faster than thought. But the eruption was only beginning. Over the next 60 hours, 60 unrelenting hours, Novarupta would expel approximately 3 cubic miles of material. To put that in perspective, this was 30 times larger than the 1980 eruption of Mount St. Helens. It was the largest volcanic eruption of the entire 20th century. And it was happening in one of the most remote corners of North America. The ash cloud spread with terrible efficiency. Winds carried it eastward across the Alaska Peninsula, across Shelikof Strait, toward the island of Kodiak. By evening of June 6th, day had turned to night. Ash began falling on Kodiak like snow, gray, suffocating, relentless snow that would not melt. In the town of Kodiak, population 500 souls, panic took hold. The darkness was absolute. Streetlights became useless, their glow absorbed by the choking ash. Breathing became difficult. Eyes burned. The ash infiltrated everything: homes, lungs, water supplies. Roofs began to collapse under the accumulating weight. The captain of the revenue cutter Manning, anchored in Kodiak Harbor, made the decision to evacuate. Through darkness so complete that navigation was done entirely by instinct and prayer, he ferried terrified residents from the collapsing town to his ship. They huddled on deck, faces covered with wet cloths, as ash continued to fall around them like judgment itself. Back at the eruption site, something even more catastrophic was unfolding. Mount Katmai, 6 miles to the east of Novarupta, was collapsing. The magma chamber beneath Katmai had been drained by the eruption at Novarupta. The two were connected underground, part of the same vast reservoir of molten rock. As magma evacuated through the Novarupta vent, the support beneath Katmai's summit vanished. On June 7th, the entire top of Mount Katmai, thousands of feet of rock and ice, fell inward, creating a caldera nearly 2 miles wide and over half a mile deep. It was as if some cosmic hand had reached down and scooped out the mountain's heart. The sound of this collapse was heard as far away as Fairbanks, 300 miles to the north. For 3 days, the eruption continued. For 3 days, the earth poured out its interior, reshaping the landscape, burying valleys, creating a new and terrible geography. And when it finally stopped, when the fury finally exhausted itself and silence returned to the Alaska Peninsula, the world that remained was unrecognizable. 40 square miles of verdant valley had been buried under ash deposits up to 700 feet deep. The forests were gone, the rivers were gone, the animals were gone. In their place lay a smoking, steaming wasteland, a desert created in a matter of hours. The people of Katmai village, safe in Prairieville, learned that their instincts had saved them. Their homes, their church, their entire community lay buried beneath ash so deep that nothing remained visible. Not a rooftop, not a chimney, nothing. The earth had spoken. And its message was absolute. When the ash finally stopped falling, silence descended upon the Alaska Peninsula like a shroud. It was not the silence of peace. It was the silence of absence. The absence of birdsong, of wind through leaves, of water rushing over stones. The world had been muted, buried beneath a blanket of gray that stretched as far as the eye could see. For 4 years, no one dared venture close to what had been the Ukak River Valley. The eruption had ceased, but fear lingered. Ash continued to settle from the atmosphere for months, circling the globe, creating spectacular sunsets as far away as London and New York. Atmospheric scientists noted a measurable drop in global temperatures, proof that this remote eruption had touched the entire planet. But in Alaska itself, the land seemed dead. Then, in 1916, the National Geographic Society organized an expedition. They wanted to see what the Earth had created, to document what one of nature's most violent acts had left behind. Leading this expedition was a botanist named Robert Griggs, a man of science, but also a man capable of wonder. What Griggs and his team discovered would astound the scientific world. When they finally reached the buried valley in July of 1916, they stood at its edge and could not believe their eyes. Before them stretched a landscape utterly alien, utterly transformed. The valley floor, once carved by a river through green forest, now lay buried under deposits of volcanic ash and pumice that reached in some places 700 feet deep. 700 feet. The height of a 70-story building, laid flat across 40 square miles. But it was not the depth that stopped them in their tracks. It was what was happening on the surface. From countless fissures and cracks in the ash, steam and gas erupted skyward in towering plumes. Thousands of them. Tens of thousands of them. Fumaroles are called vents where superheated groundwater, turned to steam by the still cooling ash deposits below, found its way to the surface. Griggs stood transfixed. He later wrote in his journal, "The whole valley as far as the eye could reach was full of hundreds, no thousands, literally tens of thousands, of smokes curling up from its fissured floor. He named it quite simply the Valley of 10,000 Smokes. It was and remains one of the most extraordinary geological features on Earth. The steam wasn't merely picturesque. The temperatures at the fumaroles were astonishing. At some vents, Griggs measured temperatures exceeding 1,200 degrees Fahrenheit, hot enough that when he thrust a wooden stick into a fissure, it burst into flames within seconds. The ground itself was an oven, baking from within, releasing the residual heat of the apocalypse that had created it. The team explored carefully, testing the ground before each step. In some places, the ash had cooled and solidified into a crust capable of bearing weight. In others, it remained loose and treacherous, ready to give way and plunge an unwary explorer into superheated depths below. They mapped the valley, photographed the fumaroles, collected samples of the ash and pumice. The material was lightweight, porous, filled with tiny gas bubbles frozen in time, evidence of the violent degassing that had occurred during the eruption. When they examined it under microscopes back in their laboratories, they found glass shards, crystals of feldspar, and quartz, fragments of the Earth's deep interior brought suddenly and violently to the surface. Griggs also located Novarupta itself, the true source of the eruption. It appeared as a small dome of volcanic rock, barely 100 feet high, utterly unremarkable in appearance. That such a modest feature could have produced such catastrophic results seemed almost impossible. Yet the evidence was irrefutable. 6 miles away, they gazed upon the collapsed summit of Mount Katmai. Where once a peak had stood, there now yawned a vast caldera, its walls sheer and forbidding, a lake beginning to form at its bottom as meltwater accumulated. The caldera was so large that Griggs calculated the entire Washington Monument could be placed inside it and still not reach the rim. As the expedition continued its work through the summer of 1916, Griggs began to understand the broader significance of what they were documenting. This was not merely a local catastrophe. This was a window into processes that had shaped the Earth for billions of years. Volcanic eruptions had built the continents, created the atmosphere, possibly even delivered the water that filled the oceans. This valley, this desert of ash and steam, was creation and destruction made visible. In his reports back to the National Geographic Society, Griggs argued passionately for the preservation of this landscape. This was a natural laboratory, he insisted, a place where scientists could study volcanic processes, where future generations could witness the raw power of geological forces. The valley was still changing, still evolving, and it deserved protection. His advocacy succeeded. On September 24, 1918, President Woodrow Wilson signed a proclamation establishing Katmai National Monument, protecting more than 1 million acres of the Alaska Peninsula. It was an act of remarkable foresight, preserving not beauty in the conventional sense, but significance, scientific value, and the humbling reminder of forces beyond human control. Over the following decades, scientists would return again and again to the Valley of 10,000 Smokes. They would measure the gradual cooling of the fumaroles, document the slow return of vegetation at the valley's edges, study the way water began to carve new channels through the ash. The valley became a reference point, a comparison for understanding other volcanic events around the world. When Mount St. Helens erupted in 1980, geologists immediately thought of Katmai. When Pinatubo erupted in the Philippines in 1991, they remembered the lessons learned in that remote Alaskan valley. But perhaps the most profound lesson was this: the Earth does not ask permission. It does not consult calendars or consider human plans. It operates on timescales that dwarf human history, driven by forces that render our greatest engineering feats trivial by comparison. The Valley of 10,000 Smokes stands as testament to that truth. A desert created in days, a landscape transformed in hours, a reminder written in ash and stone. To stand in the Valley of 10,000 Smokes is to stand at the surface of a story that begins 60 miles beneath your feet. The eruption of 1912 was not random. It was not the Earth's caprice or divine anger. It was, instead, the inevitable conclusion of processes set in motion millions of years ago, when continents began their slow dance across the planet's surface. Let us descend, then, into the depths and understand what built this desert of ash. The story begins with the Pacific Ocean floor. Imagine it not as static, but as a conveyor belt of rock continuously created at mid-ocean ridges, and inexorably moving westward at the pace of a growing fingernail. This is the Pacific Plate, one of the largest tectonic plates on Earth, and it has been traveling for eons.
Beneath the cold waters of the northern Pacific, a colossal geologic plate, the Pacific Plate, is on a collision course with a continent.
When it reaches the coast of Alaska, it doesn't just stop. It dives, sliding beneath the massive North American plate in a process called subduction. This journey downward is anything but smooth. The two plates grind against each other, unleashing the seismic energy of earthquakes. But the real transformation happens deeper down, where physics borders on alchemy. As the Pacific Plate plunges deeper, it carries water locked within its minerals. At depths of 60 to 100 miles, the intense heat and pressure force this water out. This liberated water rises into the hot mantle rock above, and like a magic ingredient, it lowers the rock's melting point. The mantle begins to melt, forming magma. This molten rock is less dense than its solid surroundings, so it begins a slow, determined ascent, gathering over thousands of years in vast underground chambers. Beneath what we now know as Mount Katmai and Novarupta, one such chamber grew to an immense size. Scientists estimate it held about 3 cubic miles of magma, a superheated reservoir simmering at over 1,800 degrees Fahrenheit, charged with explosive volcanic gases. For centuries, this system was in a tense equilibrium, the weight of the overlying rock just barely containing the immense pressure from below. But in nature, such balance is temporary.
In the years leading up to 1912, something changed.
Perhaps a new surge of magma from below increased the pressure, or maybe the roof of the chamber weakened. Whatever the final trigger, the result was inevitable. The pressure finally overcame the strength of the rock above. The magma found a path to the surface, and what had taken generations to accumulate was unleashed in just 60 hours. The sheer violence of the eruption came down to the magma's chemistry. It was rhyolitic thick, sticky, and rich in silica. As it rushed toward the surface, the dissolved gases trying to escape couldn't bubble out gently. Instead, they exploded, shattering the magma into billions of fragments, from house-sized boulders to particles finer than dust. This explosive fragmentation powered a terrifying eruption column that rocketed 15 miles into the atmosphere. This wasn't solid rock being thrown upward. It was a turbulent, expanding mixture of superheated gas and ash. When this column grew too dense to support its own weight, gravity took over. It collapsed back to Earth, not as gentle rain, but as pyroclastic flows, scorching avalanches of gas and ash moving at highway speeds, incinerating everything in their path. These flows surged through a nearby river valley, filling it up to 700 feet deep with searing hot debris. The land was utterly transformed, buried under a new, sterile landscape. As the ash settled, it was so hot that when rain and snowmelt seeped into it, the water instantly flashed to steam, venting through countless cracks and fissures. This created a surreal, otherworldly scene that would later be named the Valley of 10,000 Smokes. But the drama wasn't over. 6 miles away, the summit of Mount Katmai, a 12,000-foot peak, began to collapse. With its underlying magma chamber now drained by the eruption at Novarupta, the mountain's foundation was gone. Over the course of the eruption, the entire peak fell in on itself, creating a 2-mile-wide, 2,000-foot deep crater or caldera. It was a stunning demonstration of interconnectedness. This wasn't two separate eruptions. It was one massive volcanic system expressing its fury through two different vents. This realization revolutionized volcanology. Before Katmai, scientists viewed volcanoes as isolated mountains. The 1912 event proved that vast, complex plumbing systems can connect volcanoes for miles underground. It taught us that what we see on the surface is often just a small part of a much larger, hidden story. The eruption's impact reached far beyond Alaska. It injected enormous amounts of sulfur dioxide into the stratosphere, which formed a haze of sulfuric acid aerosols that spread across the globe. This haze reflected sunlight back into space, causing the northern hemisphere to experience a measurable drop in temperature for the next year. Katmai became a crucial case study, a natural experiment proving that a single large volcanic eruption could temporarily alter the entire planet's climate. Today, the Valley of 10,000 Smokes is silent. The fumaroles have cooled, and life is slowly returning to the edges of the ash flow. But the evidence of 1912 is written in the stone, a stark and powerful reminder of the forces at work beneath our feet. It shows us that our planet is not a static, solid rock, but a dynamic, restless heat engine. The 1912 eruption wasn't just a disaster. It was a lesson from the Earth itself. A story of creation and destruction that continues to teach us about the world we inhabit. Thanks for watching, and be sure to subscribe for more journeys into our planet's most incredible stories. In the aftermath of catastrophe, we often measure loss in numbers. 3 cubic miles of material erupted. 40 square miles buried. 700 feet of ash deposited. These figures are precise, scientific, irrefutable, but they tell only part of the story. The other part belongs to those who lived through it and to those who did not. The human toll of the 1912 eruption was remarkably minimal. No deaths were directly attributed to the eruption itself. This fact stands in stark contrast to other volcanic disasters throughout history. Pompeii, Krakatoa, Mount Katmai, where thousands perished. The remoteness of the Alaska Peninsula, the sparse population, and crucially, the warnings provided by days of earthquakes allowed people to escape. But escape is not the same as survival unscathed. The Aleutic families who fled Katmai village left behind everything they could not carry. Homes built by their grandparents. Tools passed down through generations. Fishing gear that represented their livelihood. Sacred objects. Photographs. The accumulated physical evidence of lives lived in that place. When they learned that their village lay buried under ash so deep that not even the church steeple remained visible, they understood that return was impossible. There was nothing to return to. Their community, as it had existed, was erased. They settled in Prairieville and Douglas and other small settlements along the coast. They rebuilt, as humans always do. But the elderly among them would spend the rest of their days speaking of Katmai not as it was buried beneath ash, but as they remembered it, green and alive with salmon running in the streams and the smell of spruce in the air. For them, the eruption had destroyed not just a place, but a world. The villages of Savanoski and Kukak suffered similar fates. The residents evacuated in time, packed into boats, watching the skies darken behind them as they rowed toward safety. Their settlements, too, were buried. The ash fall in some areas exceeded 2 feet, then 3, then more. Roofs collapsed under the weight. Walls buckled. By the time the eruption ended, these communities had been entombed. Archaeological excavations decades later would uncover fragments of these lost villages. A metal stove here, a collapsed timber there, everyday objects transformed into artifacts by a burial more thorough than any tomb. But if the human population was sparse and mostly spared, the same cannot be said for the land's other inhabitants. The brown bears of the Katmai region had lived there for millennia, fishing the abundant salmon runs, hibernating in dens carved into hillsides, raising their cubs in the relative safety of the remote peninsula. The eruption gave them no warning they could understand, no time to adapt. Those caught in the pyroclastic flows died instantly, incinerated where they stood. Those who survived the initial eruption faced a transformed landscape utterly incapable of supporting them. The rivers were choked with ash, the salmon runs destroyed. The vegetation they depended on was buried. Starvation claimed many in the months that followed. Scientists studying the region years later found bare bones scattered across the ash deposits, silent testimony to creatures who had outlasted ice ages and predators but could not outlast the Earth's fury. The moose, the caribou, the wolves all suffered similar fates. The eruption did not discriminate. It simply transformed the land from habitat into wasteland, and in doing so, sealed the fate of anything unable to flee fast enough or far enough. Even the rivers themselves became casualties. The Ukek River, which had carved its valley over thousands of years, vanished beneath the ash. When water eventually returned from rain from snowmelt, it could not find its old channel. It carved new paths across the ash deposits, creating temporary streams that shifted with each season. The geography had been reset. On Kodiak Island, 100 miles from the eruption, the ash fall created a different kind of disaster. 2 to 3 feet of ash accumulated on the island, burying grasslands, contaminating water sources, coating everything in a suffocating gray blanket. The Kodiak bear population, isolated on the island and numbering perhaps 3,000 individuals, faced potential extinction. Their food sources, salmon, berries, vegetation, were devastated. Many bears died that first winter. Others became desperate, wandering closer to human settlements, searching for anything edible. But nature, when given time, possesses remarkable resilience. The ash, though initially destructive, proved to be rich in minerals. As it weathered and broke down over subsequent years, it enriched the soil.
Vegetation returned, first as scattered pioneers, then as expanding colonies.
The salmon runs recovered as rivers cleared. And slowly, incrementally, the bear population rebounded. It took decades, but it happened. Life found its way back.
The story of recovery was not universal, however.
Some species never returned to certain areas. Some ecosystems shifted permanently, establishing new equilibria different from what had existed before. The eruption had not just destroyed, it had reorganized, reshuffled, created new rules for survival. In Kodiak Town itself, the human experience of the eruption was one of terror and uncertainty. The darkness that descended on June 6th was absolute. People described it as thicker than any night, as if the sun had been extinguished. Ash fell continuously, accumulating on roofs until they groaned under the weight. Several buildings collapsed.
Breathing became difficult.
The ash was fine enough to penetrate even tightly sealed buildings, coating lungs, causing coughing and respiratory distress. People tied wet cloths over their faces, huddled indoors, and waited for the nightmare to end. The Manning, that revenue cutter in the harbor, became a refuge. Captain Perry, risking his ship in near-zero visibility, ferried more than 500 people from the collapsing town to the relative safety of his vessel.
For 3 days they remained there, anchored in the harbor,
as ash continued to fall around them and the town they knew disappeared beneath gray drifts. When the eruption finally ceased and the ash stopped falling, when daylight gradually returned and they could see what remained, many wept. Their town still stood, damaged but salvageable, but the world around it had changed. The familiar landscape was gone, buried under ash that would take months to clear and years to fully weather away.
In the broader world far from Alaska, the eruption barely registered.
The year 1912 was consumed by other concerns. Political tensions in Europe,
the sinking of the Titanic 2 months earlier, the approach of a war that would reshape the world. A volcanic eruption in a remote corner of Alaska merited a few newspaper articles, a moment of curiosity, then was forgotten.
But for those who lived through it, who lost their homes or their communities or their loved ones to starvation and displacement, the eruption was everything.
It was the dividing line between before and after, between the world as it was and the world as it became.
And for the land itself, for that 40 square miles buried beneath hundreds of feet of ash, it was a transformation so complete that a new name was required.
It was no longer a valley carved by water and time. It was the Valley of 10,000 Smokes, a desert born from fury, a testament to forces that care nothing for what we build or where we choose to live. The Valley of 10,000 Smokes did not remain static after its violent birth.
It became instead a stage upon which the earth performed a slow symphony of transformation. When Robert Griggs returned in the summers following 1916,
he documented changes that occurred year by year, season by season.
The fumaroles, those thousands of steam vents that had given the valley its name, were gradually diminishing.
The ash deposits below were cooling, releasing their stored heat more slowly with each passing year.
In 1916, the valley steamed so vigorously that visibility was often reduced to mere yards. By 1920, some of the smaller vents had ceased entirely. By 1930, large sections of the valley floor had cooled enough that the fumaroles became intermittent. By the 1950s, most had stopped altogether.
Today, the Valley of 10,000 Smokes is quiet. The steam has faded.
What remains is a stark, lunar landscape of ash and pumice, carved by wind and the patient work of water. The name persists, but the phenomenon it described has largely vanished. A reminder that even geological features exist on timescales measured in decades, not eternities. Yet the valley continues to teach.
Scientists discovered that the ash deposits, though appearing uniform from a distance, actually consist of distinct layers,
each representing a different phase of the eruption. Some layers are fine-grained, composed of ash that fell from the eruption column like snow. Others are coarse, filled with pumice fragments the size of fists, ejected with such force that they fell hot enough to weld together upon landing. These welded tufts, as they're called, became objects of intense study.
They represent a snapshot of the eruption at its most violent, material so hot, under such pressure, that it fused into solid rock almost immediately upon deposition.
Examining them reveals details about eruption temperatures, gas content, and the dynamics of pyroclastic flows. One discovery particularly fascinated researchers. Within the ash deposits were tree molds, hollow tubes where trees had stood when the pyroclastic flows arrived.
The superheated ash had wrapped around the trees, vaporizing the organic material but preserving the shape. When scientists excavated these molds, they found charcoal fragments at the bottom, all that remained of forests that had stood for centuries. The charcoal allowed for carbon dating, confirming the timing of the eruption and providing data points for understanding the region's geological history. It also served as poignant evidence of how quickly destruction had occurred. These trees hadn't burned slowly. They had been consumed in seconds, buried before they could even fully combust. Water, too, told stories in the valley. As rain and snowmelt began to flow across the ash deposits, they carved channels, not the gentle, meandering streams of a mature landscape, but sharp, steep-walled gullies cutting into the soft ash with startling efficiency. Scientists studying these erosion patterns gained insights into how landscapes evolve after catastrophic burial events. They observed that water preferentially carved along weaknesses in the ash, cracks, zones where different eruption phases met, areas where the ash was slightly less compacted. Within years, a dendritic network of streams had begun to form, radiating outward like the branches of a tree, each channel deepening with every rainfall, every spring thaw. Some of these cuts exposed the buried landscape beneath the ash, the old valley floor, complete with preserved tree stumps and the remnants of the original soil. Standing at the bottom of one of these erosion channels was like stepping back in time to the moment before the eruption when green still existed here. The valley also became a laboratory for understanding how life returns to devastated landscapes. At the margins where ash deposits were thinner, hardy pioneer plants began to appear within a decade of the eruption. Fireweed, with its brilliant purple blooms, was among the first. Then grasses. Then small willows, their roots finding purchase in the enriched soil created as the ash weathered and broke down. These plants were not merely surviving. They were beginning the long process of soil creation. Their roots broke apart the compacted ash. Their fallen leaves added organic matter. Microorganisms followed, decomposing the organic material, cycling nutrients, slowly transforming sterile ash into something capable of sustaining more complex life. By the 1950s, the edges of the valley supported scattered shrubs and even small trees. By the 1970s, moose had returned, browsing on the new growth. By the 1990s, bears once again walked the valley margins, though they avoided the central ash fields where nothing grew and nothing could survive. This process of ecological succession, the gradual return of life to barren land, became a textbook example studied by biologists worldwide. The Valley of 10,000 Smokes provided a controlled natural experiment in how ecosystems rebuild after total devastation. But the valley's greatest contribution to science may be its role in understanding volcanic hazards more broadly. Because the 1912 eruption occurred in a relatively accessible location, with excellent preservation of deposits and minimal human interference, it became a reference point for volcanologists studying eruptions elsewhere. When scientists examined deposits from the 79 AD eruption of Mount Vesuvius, they compared them to Katmai. When they studied the catastrophic eruption of Mount Pinatubo in the Philippines in 1991, they used Katmai as a model for understanding pyroclastic flow dynamics. When they assessed volcanic risks in populated areas, near Mount Rainier in Washington, Mount Fuji in Japan, Popocatépetl in Mexico, they asked, could this produce a Katmai-scale eruption? What would the consequences be? The answer, in most cases, was sobering. A Katmai-scale eruption near a major population center would be catastrophic beyond measure. The 1912 eruption occurred in one of the most remote regions of North America, and still it buried 40 square miles under hundreds of feet of ash, altered global climate, and created a desert that persists to this day. Imagine such an event near Seattle or Tokyo or Mexico City. This is why the Valley of 10,000 Smokes matters beyond its own boundaries. It is a warning written in the clearest possible language, the language of ash and buried forests and steam that rose from superheated ground for decades. The Earth is not tame, it is not controlled, and the forces that created this valley still exist, dormant but not extinct, beneath volcanic regions around the world. In 1980, Mount St. Helens erupted in Washington state, producing approximately 1/10 the volume of material that Katmai had produced. 57 people died. Hundreds of square miles of forest were leveled. The economic damage exceeded $3 billion, 1/10 the scale of Katmai, and it was considered a national disaster. Scientists standing in the Valley of 10,000 Smokes after the St. Helens eruption understood something profound. They were looking at what might have been scaled up 10 times. Had St. Helens been located in a more remote region, or had Katmai occurred near a city? The valley thus serves dual purposes. It is both a monument to destruction and a classroom for prevention. The lessons learned here about eruption dynamics, about warning signs, about the importance of monitoring and evacuation, have saved countless lives in subsequent volcanic crises around the world. When Pinatubo showed signs of unrest in 1991, scientists recognized the patterns from historical eruptions, including Katmai. Thousands were evacuated in time. When Age of geological erupted in Iceland in 2010, disrupting air travel across Europe, scientists used knowledge gained from studying Katmai's ash dispersal to model how the ash cloud would spread. The Valley of 10,000 Smokes, silent now, its steam vents cold, its fumaroles extinct, continues to speak. It speaks through the research papers written about it, through the photographs documenting its slow evolution, through the samples collected and analyzed in laboratories around the world. It speaks, most of all, through the simple fact of its existence. A landscape transformed utterly. A desert created from paradise. A reminder carved in stone that the Earth's fury, when unleashed, knows no bounds. The people of Katmai village had fled based on instinct and ancestral knowledge, interpreting the language of earthquakes and fleeing animals. They survived through wisdom passed down across generations. But what of communities elsewhere, where such knowledge had been forgotten or never existed? What of cities built in the shadows of sleeping volcanoes, where millions lived unaware of the forces beneath their feet? The answer required a new approach, one that would transform volcanology from a descriptive science into a predictive one. The Alaska Volcano Observatory was established in 1988, more than 7 decades after the Katmai eruption. Its mission was deceptively simple: monitor the state's many volcanoes and provide warnings before they erupted. But achieving this mission required technology, expertise, and an understanding of volcanic behavior that had taken generations to accumulate. Today, Mount Katmai and its neighbors are among the most closely watched volcanoes on Earth. Seismometers, instruments that detect the slightest tremor in the Earth, are positioned across the Katmai region. They listen constantly for the telltale signs of magma movement underground. When magma rises, it fractures rock, generates earthquakes, creates vibrations that propagate through the Earth's crust. These earthquakes have distinctive signatures, different from the grinding of tectonic plates or the settling of geological structures. Scientists have learned to read these signatures the way physicians read electrocardiograms. A particular frequency here, a clustering of events there, a gradual increase in intensity over days or weeks. Each pattern tells a story about what is happening miles below the surface. GPS stations measure ground deformation with astonishing precision. Volcanoes, when they prepare to erupt, often swell as magma accumulates in chambers below. This swelling can be measured in centimeters, sometimes millimeters, detected by comparing the position of GPS receivers over time. At Katmai, such measurements revealed something fascinating. The ground is still moving. More than a century after the eruption, subtle deformation continues, suggesting that magma is still present in the system below, still cooling, still settling. The volcano is not extinct. It is resting. Gas monitoring provides another window into volcanic behavior. Volcanoes emit gases even when they're not erupting, primarily water vapor, carbon dioxide, and sulfur dioxide. Changes in the composition or volume of these emissions can indicate that fresh magma is entering the system from below, bringing with it dissolved gases from the Earth's mantle. Scientists fly over Katmai periodically, using instruments that can detect and measure these gases remotely. They've discovered that Novarupta, that modest dome that produced such catastrophic results in 1912, still emits trace amounts of volcanic gases. The furnace below has cooled, but it has not gone cold. Satellite imagery adds yet another layer of observation. Thermal cameras can detect heat anomalies invisible to the naked eye. Radar interferometry can measure ground deformation across entire regions, creating detailed maps of areas that are rising or subsiding. All of this data flows into the Alaska Volcano Observatory, where scientists analyze it, searching for patterns, watching for changes that might herald another eruption. And the watching is not confined to Katmai alone. Alaska is home to more than 130 volcanoes, at least 50 of which have been active within recorded history. They form a vast arc along the southern coast and the Aleutian Islands. The surface expression of the Pacific Plate is relentless. Subduction beneath North America. These volcanoes do not erupt on human schedules. Mount Redoubt erupted in 2009, sending ash plumes 50,000 feet into the atmosphere, disrupting air traffic, threatening communities. Pavlov has erupted more than 40 times since the 1700s. Most recently in 2021, Shishaldin erupts so frequently that pilots flying the Aleutian route know to watch for its glow on dark nights. Each eruption provides data. Each eruption refines our understanding. And each eruption reminds us that prediction, despite all our technology, remains an imperfect science. The truth is this: we have become much better at knowing when a volcano is waking up. The instruments are sensitive enough to detect unrest weeks or months before an eruption. Earthquake swarms, ground deformation, increased gas emissions. These precursors give us time. But we cannot yet predict with certainty when an eruption will occur, or how large it will be. Nature does not operate on timelines convenient for evacuation plans and emergency management. Some volcanoes show clear warning signs and then go back to sleep without erupting. Others erupt with minimal warning. Mount Pinatubo in the Philippines gave scientists several weeks of warning before its catastrophic 1991 eruption. Monitoring teams detected the precursors, convinced authorities to evacuate tens of thousands of people, and saved countless lives. It was a triumph of volcanic monitoring. But other eruptions have been far more sudden. Ontake in Japan erupted in 2014 with almost no warning, killing 63 hikers who happened to be on the mountain that day. The precursors were there in retrospect, but so subtle that they were not recognized in time. This is the reality scientists at the Alaska Volcano Observatory live with every day. They watch their instruments, they analyze their data, and they make decisions that could mean life or death for communities in the shadow of these sleeping giants. The work is painstaking, often monotonous. Years can pass with nothing but routine measurements, background seismicity, normal gas emissions. Then suddenly something changes. An earthquake swarm begins at Mount Spur. Ground deformation accelerates at Mount Makushan. Gas emissions spike at Mount Vyacheslav. And decisions must be made. Is this the beginning of an eruption sequence? Should aviation color codes be raised? Should communities be notified? The cost of a false alarm is measured in economic disruption and eroded public trust. The cost of missing a real event is measured in lives. At Katmai, the likelihood of another major eruption in our lifetimes is considered low but not zero. The magma chamber that fed the 1912 eruption was largely evacuated. Refilling such a chamber takes time, perhaps thousands of years. But the volcanic system remains active. Small earthquakes occur periodically. Gas emissions continue. The ground still moves. Geologists studying the region have found evidence of earlier eruptions at Novarupta, events that occurred thousands of years before 1912. The geological record suggests that major eruptions in this area occur every few thousand years, infrequently on human timescales, regularly on geological ones. So the watching continues. The seismometers listen. The GPS stations measure. The satellites observe. And scientists at the Alaska Volcano Observatory maintain their vigil, knowing that the earth beneath their feet is not truly sleeping, merely resting between acts of a drama that has been playing out for millions of years. In this way, the legacy of the 1912 eruption extends far beyond the Valley of 10,000 Smokes. It extends into the present and the future, into monitoring rooms where screens display real-time data from dozens of volcanoes, into emergency management offices where evacuation plans are updated and refined, into the homes and businesses of people living in volcanic regions around the world. We cannot prevent eruptions. We cannot control the Earth's inner fire. But we can watch and we can learn, and when the giants wake, we can sometimes get out of the way in time. That is the promise of modern volcanology. And it is a promise built, in part, on lessons written in the ash of a remote Alaskan valley more than a century ago. Stand today at the edge of the Valley of 10,000 Smokes, and you will encounter silence. The steam is long since faded. The fumaroles are cold. What remains is a landscape of ash and pumice stretching toward distant mountains, carved by wind and water into shapes that seem almost deliberate, as if the earth were an artist working in shades of gray. More than a century has passed since the eruption.
an entire human lifetime.
And yet the valley remains largely barren, a desert persisting in a region where rain falls abundantly and forests grow tall. This is the paradox of catastrophic change. Some wounds heal quickly, while others endure for generations.
Life has returned to the margins. Grasses cling to the valley's edges. Willows have established tentative footholds where erosion has exposed older soil beneath the ash. In summer, wildflowers bloom in scattered patches, splashes of color against the monochrome landscape.
Bears pass through occasionally, following the same ancient routes their ancestors walked, now elevated hundreds of feet by the ash beneath their paws. But the heart of the valley remains empty. The ash is too deep, too sterile, too recently deposited for forests to reclaim what was lost. Scientists estimate it will take thousands of years before the valley resembles what it was in June of 1912. Thousands of years, longer than recorded human history. Longer than agriculture or written language or cities have existed. The eruption lasted 60 hours. Its consequences will persist for millennia. This is what the Valley of 10,000 Smokes teaches us, in the end. It teaches humility. We build our cities and imagine they will stand forever. We alter landscapes and believe we control nature. We develop technologies that seem to place us above the natural world, insulated from its forces. And then the Earth reminds us otherwise. A single volcanic eruption in a remote corner of Alaska, buried 40 square miles under hundreds of feet of ash, altered global climate, and created a desert that endures to this day. It did so without malice, without intention, simply as an expression of processes that have been shaping this planet for billions of years. We were here for none of that ancient history. We will be here for none of the distant future. We exist in the thinnest sliver of geological time, walking on a crust that floats atop molten rock, living on a planet that is dynamic, restless, and utterly indifferent to our plans. The Valley of 10,000 Smokes stands as testament to this truth. It is not a monument to human achievement or failure. It is a monument to the Earth itself, to its power, its persistence, its capacity for both creation and destruction. And it is beautiful in its way. Beautiful in the starkness of its ash fields, in the sharpness of its erosion channels, in the silence that speaks louder than any words. Those who visit the valley today, tourists, scientists, pilgrims seeking connection with forces greater than themselves, often report feeling small. Not diminished, but properly sized. They stand at the edge of this ash desert, looking out across a landscape that should not exist and yet does. And they understand something fundamental about their place in the universe. We are temporary, the Earth endures. The mountains will rise and erode. The glaciers will advance and retreat. The volcanoes will sleep and wake. And through it all, the Valley of 10,000 Smokes will remain, slowly transforming, slowly healing, carrying forward the story of that June day in 1912 when the Earth tore itself apart and created a desert from paradise. This is the fury of the Earth. Not anger, but process. Not punishment, but physics. The same forces that built the continents and filled the oceans with water can in moments reshape landscapes beyond recognition. We cannot stop these forces. We can only witness them, study them, and remember. And perhaps, if we are wise, we can learn to live with them, not in defiance, but in respect.